fun topic and such a, I'm really excited to be talking about visualization in astronomy and astrophysics because we're really undergoing, every field is in a different state for how it's using this incredible silicon-enabled revolution. So how we're using both these new data sets that we're getting and also this massive quantity of data that we've been hearing about tonight. As Eric mentioned, and as Chris mentioned, I'm the director of the 5th generation of the Sloan Digital Sky Survey. And the Sloan Digital Sky Survey really was an inflection point in the history of astronomical surveys because of the invention of the CCD and the ability to take these digitized images that you can analyze across large swaths of sky. So this was a huge change in the amount of data that astronomers were used to. Of course, it started on the Sloan telescope and has now leapt to Carnegie's DuPont telescope, so now we are an all-sky survey. And I just want to highlight, 21st century data sets sort of look something like this. So instead of scanning little patches of the sky, we're scanning the entire sky. And we're not just scanning the sky once. We're scanning it many times. So I'm showing here the pattern of observations that SDSS-5 will take. And every single time a piece of this image gets darker, it means we revisited that part of the sky again. So not only are we looking at massive quantities of data in space, but we're also looking at massive quantities of data in time as well. And this time domain is a huge area in astrophysics where we're sort of exploring variations of objects on seconds, milliseconds, years, megayears, gigayear timescale. And so what do we do with all of this data? So as you heard before, this is just the growth just in the SDSS-4 of the amount of data that SDSS has taken. Now these are small little terabytes here, so we're going up to petabytes. And of course, next generation surveys are going orders of magnitude larger than this. So the quantity of data is increasing, as we've heard. But it's also the character of the data. So raise your hand if you know what this is. It's a galaxy. Okay? So this is what a galaxy looks like, right? But a galaxy is not just a two-dimensional entity, right? It's a three-dimensional entity, but it's also physically a very high-dimensional structure. And so what we're showing here is a data cube where every single piece of this data cube, we're showing an image and also kind of peering through that galaxy in frequency. So now you're not just seeing the two-dimensional image of the galaxy, but you're also seeing the spectra. Sort of imagine the rainbows that the sun makes after a rainstorm. You're seeing the three-dimensionality of that data in this physical space. And so every single pixel in that image is a spectrum or a rainbow of that part of the galaxy, which encodes the physics of the galaxy itself. Now, what do you do when you have a very complicated new data set that is pretty tricky to understand? So first of all, you spend a lot of time coding things up and trying different things yourself, but at some point, you go talk to Chris and his colleagues and see what crazy stuff that they've got going, because they're just focused on so many different tools. And so we visited the SKI Institute a few years ago and started a project that this is one of those data cubes, so if you took just one slice out of this image, that would look like this simple galaxy, okay? But now you see the galaxy is this very detailed structure where frequency is on the axis going sort of diagonally in the page here. And what we're trying to do is we're trying to use new sophisticated methods to find features in this complicated data cube. So you have a blob of gas that you want to understand. What is that blob? Is that blob of gas coming from a star that has exploded? Is it coming from a shock that has been created by some merger? And in order to do that, you have to separate out the noise from the real features. And so we're using like a network analysis that John just mentioned, and some very sophisticated topological structures. This is in collaboration with Bei Wang, who is a faculty member at SKI, and her graduate student is part of the Carnegie Venture Grant Program. We are analyzing, this is SDSS data, MANGA data in the bottom right here, and in the upper left I'm just showing a schematic of how we separate out different features in a topological plane. Now that's on the data side, so that's how we're using different advanced techniques to understand the data better. But what about on the theory side? And that's my sort of intellectual home is in theoretical astrophysics. On the left here, I'm showing the temperature map of galaxies as they form, starting at the earliest parts of the universe and evolving all the way down to the present day. And you see it kind of looks like one of these brain networks that Chris just showed. There's this network of filaments and voids, and you have galaxies that are blowing hot bubbles around them. The pink there is gas that's 10 to the 7 Kelvin. It's very hot. And even the blue is much cooler gas, but still 10 to the 3. So what's happening there is that galaxies are blowing up, okay? And in the other panel here on the right, I'm showing a galaxy that is being ablated by falling into a bigger system of galaxies. And this is a calculation that a former Carnegie Fellow, Stephanie Tunison, performed. See if I can get that to play again. Oh, nope. Oh well. There we go. Let's get it a little bit. I'm a keynote person, not a PowerPoint. There we go. Oh, there we go. So you see that galaxy is getting ablated as it falls into a much denser system. And so the shape of that galaxy is changing, but also the gas is getting thrown away. Now, these are beautiful movies, right? I think they're pretty cool. They're pretty to look at. But what do we do when we compare galaxies to our predictions? We turn all of this into one number, maybe two numbers, a mass, or a rate of star formation. But clearly, you don't have to be a theoretical astrophysicist to realize there's a lot more information in these calculations. How do we extract all of that information? How do we do principled comparisons of these calculations to the observations themselves, to like those data cubes that I showed you before? And that's why we're trying to build a VisLab. So Chris showed you his Powerwall. We want to take one of these California garages and turn it into something great. This is what we are hoping to turn it into. Space, an interactive space where we can actually sit in these galaxies and in these calculations and actually try to figure out new methods for comparing these theoretical calculations to the types of data that we're getting in surveys like the Sloan Digital Sky Survey and in other smaller surveys that we're doing with our Magellan telescopes. And so that's sort of the state of the art from astrophysics, really using new techniques to both interrogate the data, discover new things, and also understand our theoretical calculations better so that we can make better comparisons between observations and data. Thanks.
Data the best. I mean, that was really awesome. Let's give it one more hand. That was really